Okay, this is an interesting question we've got here. Um, got a tank full of water, and we're trying to calculate the work to pump the water out of the spout. It's really important that you understand that they're using the concept of a floating pump. If you're not sure what a floating pump is or how it works, please watch the video in the homework um, that uh, explains how a floating pump works. And it's really important because if the water was being pumped out from the bottom, that would completely change this question. All I'd have to do is figure out the weight of the water and the distance from the bottom A to the top. D is, let's see, A is 4 and D is 4, so the distance would be 8. We'd pretty much be done. However, since we're using a floating point pump, the situation becomes much more interesting to calculate. So let's do that. First thing we need to figure out is our force. Well, let's talk about that floating pump for just a second before we get into that. So the distance, what's going to happen is a floating pump is on top, and so your distance will start getting larger and larger and larger as the water gets lower and lower and lower. So that's important. Okay, so the distance actually we're going to start pumping out is at 4 feet, and then it's going to move to 8 feet. So we'll come back to that distance, but let's work with the force for just a second. Force is mass times acceleration. And basically, it's the weight of the object. We just need to figure out how much weight we're pumping out at any given time. So let's take a look at this. Let me make this a little bit smaller. What we're going to use to calculate the weight is the density of the water and gravity and the volume. So what we have is the mass is going to be basically the kilograms of water, and we know that there is 1,000 kilograms per every cubic meter of water. So we just need to know how much cubic meters we're pumping out, and we're going to call that our volume that we're pumping out. And acceleration due to gravity is 9.8. Now, what I'm going to do here is simplify this just a little bit. I've got 9.8 times 10 to the third times our volume is our force in newtons. So how do we calculate volume as we're pumping it out? So let's take a look. It would be real easy if it was a cube, because it would just be volume at any given point would be B times C times however depth we're going to go. And what I'm going to use here is let the height at any given time be x. So that's the height from the bottom to where we're at. And what you should realize on this is A and B have equal value. That's important because we're dealing with a triangle, which means if I want to find at any given height, that it's going to be dependent on that. So in this area, if we wanted a volume, we would just need to know how thick a slice we're talking about, and that would be delta x. And again, if we were just looking at the very top, it'd be real simple. Just have a little delta x there, and away we would go. But it's changing shape as we go down. C is staying constant, so that's not going to change. But B will not stay 4 as we go down. It's getting more and more narrow. So if we let x be the height, then how wide this is at any given time will also be x. C is always staying 9, and delta x is going to be the depth of our slice of water at any given time. And I will leave that as delta x. So that is going to be our volume for any height that we're at in there. So I can now substitute that in. I might simplify it a little bit. So I've got 9.8 times 10 to the third times 9x times the depth of the water, delta x. Okay, so we're going to start off here. Now, that is our force. Now, let's talk about D. So we've got our work is going to be this force times D. Oops, it's not a times, it's 9.8 times 10 to the third times 9x delta x, the distance that the water is going to be moving up the pipe. So the minimum distance will be D, and that is 4. However, as the water goes down, we're going to have more and more depth. So what we're going to end up with is, actually it's going to be, I'm sorry, not 4. We're looking at a total depth here of 8. And it's going to be 8 minus x. And what you should notice is x can change between 0 and 4. So when the tank is full, x will be 4. As the tank goes down, the maximum distance will be 8. So as x is getting smaller, the distance that this has to travel is going to get larger. So it's really a matter of taking the summation for every conceivable delta x in here, and that's where we're going to get our integrand from 0 to 4, which is our domain for x. And I'm going to go ahead and pop this out a little bit. Let's simplify this. I'm going to do this 9.8 times 9 is 88, or 8.82 times 10 to the fourth. Why 10 to the fourth? I had 10 to the 3. If I put it as 88.2, it would be 10 to the 3. Moving over the decimal one more is 10 to the fourth. And that basically removed these constants to the front of my integrand. So now all I have to deal with is 8x minus x squared dx. So not too bad. I will leave this 8.82 times 10 to the fourth, and I'll go ahead and integrate. And I have 8x squared over 2, and that's going to reduce to 4, minus x cubed over 3, that will not reduce, from 0 to 4. So at this point, it's really just arithmetic. I'm going to be plugging that in, 8.82 times 10 to the 4, times 10 to the 4th over, when I plug in 0, that's all going to be 0. So 0 squared is 0, minus 0 cubed is 0. So we're done with that. So I don't have to worry about the subtraction. I just have to plug in the 4. So it's going to be 4 times 4 squared minus 4 cubed over 3. This I'll go ahead and plug into my calculator, and I should come up with the answer. So I'm going to start from the inside out. Basically, I have 4 cubed, 4 times 4 times 4, minus, minus 4 cubed divided by 3, enter, times 8.82 times 10 to the 4th. And that should be the work that I need to do.